It's a great pleasure to introduce Jason Hartline, who is giving his second talk in 2 days here at Brown. So many of you saw him yesterday as well, and I've already introduced him. But okay, briefly again, he is visiting us from actually right now Stanford, where he's on sabbatical, but he is a professor at Northwestern. He's been there, I don't know, 15 years, roughly. Before that, he was at Microsoft Research for quite some time, and he also did a postdoc with Avram Blum and his PhD at the University of Washington with Anna Carlin. He is kind of legendary in the field of, well, it's not listed there, but algorithmic mechanism design. He wrote the textbook, and this talk seems like it's going to incorporate lots of aspects of what I, related to algorithmic mechanism design, but apparently it's his first time giving it. So let's all, be really harsh on him. I'm just kidding. Be gentle. Okay. Thank you, Jason, for being here with us.
Awesome. Thanks so much. And yeah, as Amy said, this is the first time with this talk, so it's really new stuff. And as someone who took a deep dive into this awesome field of algorithmic mechanism design, where I've worked 20 years since my PhD on this topic, recently, I think a lot of people in algorithms have been interested in beyond case algorithms. And we've been doing a lot of that stuff in mechanism design for a long time. And so I wanted to spend some time thinking about what are the ideas from mechanism design that we've gotten very used to and got a lot of experience with that could potentially we can bring back and have a lot of impact in algorithms. And so that's sort of what we're basically lessons learned from algorithmic mechanism design applied to algorithm design is what today. This is joint work with a former PhD student at Northwestern, Alec Johnson, and a current PhD student, Anna Shah. And actually, there are 3 parts of the talk. The first 2 parts are joint with them, and then the last part, which is going to be like probably 2 minutes at the end, is has some additional co-authors I'll introduce at the time. So I'm going to be talking about online algorithms. And online algorithms, the input is revealed over time. And the algorithm has to make irrevocable decisions at every stage without knowledge of the future. And it might not be happy with its decisions in the past at some point in the future. So it's got to sort of, hopefully make decisions that are still okay when any future we see. Okay, so I'll have an input, which I'll index the time x1 through xt, and the vectors will be in bold. And we can think deterministic algorithms, family of deterministic algorithms, I'll call that A. And a randomized algorithm is just going to be a distribution over deterministic algorithms, as you might imagine. And then, we can evaluate a deterministic algorithm input. I'll just use notation A of x to be like its performance. So like this is going to be, I'm going to be doing ski renter later where we're trying to minimize costs. So A of x is going to be the cost that this algorithm gets on this input. Okay, and typically in online algorithms, we compare to the optimal offline algorithm. I'm going to write the exact same thing in a little bit different a way. So I'm going to say what happens if the algorithm knows the future. Then what was it going to do? Well, it's obviously going to do the optimal offline thing because it knows what the future is coming. So, but to me, it's going to make more sense to parameterize things by knowledge. And so if we have knowledge of the exact future, there's the optimal offline, which I'll write off of x for the sub x with the knowledge you have, and then apply to x the actual input it sees, which is the same as the knowledge it has. Okay, and then we might be interested in the randomized algorithm with the best worst case competitive ratio. Again, I'm going to be talking about costs. So I'm trying to minimize costs. And so we're going to be minimizing over all distributions over deterministic algorithms, maximizing over inputs, the ratio of the algorithm's cost to the optimal cost. So we want that to be a small. So this should look familiar to lots of people. Good. So the first thing I want to do is say that these kinds of algorithm design problems are zero-sum games. Okay, so let's see how that is. There's an adversary whose action space is all inputs. They're going to choose an input. And the algorithm's action space is all algorithms. They're going to choose an algorithm. And for a pure strategy profile, for a fixed deterministic algorithm and a fixed deterministic input, we can write off the payoff, right? It's just going to be this ratio for the adversary, which they're trying to maximize, and minus the ratio for the algorithm, which is basically trying to minimize the ratio. And the sums of the payoffs are zero. It's a zero-sum game. So good. So equilibria generally in game are mixed strategies. They're randomized algorithms, and randomizations over inputs is going to be the equilibrium of this game in general. And so let's see what that means for, and so there are going to be two properties of zero-sum games that are going to be very useful that we're going to get a lot of mileage from. Okay, so in a zero-sum game, if I found an equilibria, if I found a mixed strategy, a randomization over algorithms and a randomization over inputs where no one can improve, the adversary can't make it worse and the algorithm can't make it better, that's an equilibrium. And it turns out that every equilibrium, if there could be multiple, have the exact same value. Okay, so it's called the value of the game, and this is a property of zero-sum games only. Okay, and it turns out that if you play by your equilibrium strategy, your value is guaranteed. So if the algorithm follows this mixed strategy equilibrium, even if the adversary doesn't play an equilibrium strategy, if it does something else, the value is guaranteed. Okay, so this is a robust algorithm. It guarantees it's getting basically the worst case approximation factor. Okay, so good. So for online algorithms, this value of this game is the optimal competitive ratio. And the optimal randomized algorithm for this game is the one that basically achieves this competitive ratio. Competitive ratio is just the approximation factor term from online algorithms. So it means approximation factor. Cool. So that's basically this idea. I mean, I think it's a straightforward idea. It turns out it's going to be very useful, and it's going to illuminate some things in algorithms that we maybe haven't been thinking about so much. And so in the next 3 slides, I'm going to give you just a high-level sketch of 3 parts of the talk of what we're going to be doing. We're going to take this idea of zero-sum games and apply it 3 different times to very similar problems and make observations about online algorithms that I think are, that I haven't heard of before. And so if you've heard of them, please tell me. But these are new observations for us, and I think they're in general new. Cool. So here's the first observation. If we're playing a game against the adversary, and it's an online algorithm, so algorithm is playing over time, we can sort of tell if the adversary makes an action that is not in the support of their optimal equilibrium strategy in the game. Right? So if the adversary sort of makes mistakes in giving us a worst case input, we can tell as we go. And if they make mistakes, really what I'd like to do is not just get my old worst case value, but I should take advantage of these mistakes. In other words, if my input is not a worst case input, I would like to do a lot better. And so how can we think about doing a lot better? And that's I'm going to introduce what I'll call subgame optimal online algorithms. And that means from every point in time, given what we've done, if we just started a new game now and said, what's the best mixed Nash given where we are, we're playing optimally for that one. And so whenever the adversary makes mistakes, we enter a new subgame. We're going to play optimally. Okay, and this is going to give us improvements, and it's going to sort of not leave money on the table. And what happens is, in worst case algorithms, when the adversary makes mistakes, well, now all of a sudden the worst case has a lot of slack in it. And it's sort of sad to not eat up that slack, right? To not take advantage of it. And that's where you sometimes hear people saying, well, the worst case is too pessimistic, so I don't like worst case algorithms.
Well, I'm going to give you a worst case algorithm that always takes advantage of every mistake of the adversary to eat up that slack. Cool. And we're going to be studying the finite horizon ski renter problem as like a toy problem, which is sort of a canonical toy problem for online algorithms, where we can exactly solve for these worst cases, and we can exactly solve for the subgame optimal algorithm. And what we'll see, and in this plot, I'm not going to tell you the distribution right now, but I have a distribution over inputs. This distribution over inputs is not necessarily worst case. And I plotted if we just run the worst case algorithm not thinking about subgames optimality. That's going to be, and again, we're trying to minimize this competitive ratio. That would be the green. And if we take advantage of mistakes of the adversary for this distribution, we're going to get the orange. Okay. I'm not going to tell you what the blue is yet. I'll tell you the blue shortly. Okay, but that's, and you can see, I mean, these competitive ratios for ski renter. If you know ski renter, you know that the worst case is one minus e over e minus 1, 1.58 about, and so we're seeing on this distribution. You know, look, the bad places are what 1.5-ish, which is like close to 1.58, right? And we're getting, you know, in the 1.3, 1.33 by taking advantage of adversary making mistakes. So we're really improving on the competitive ratio here. So I thought this was good. So what I'm plotting here with the green and the orange, so the answer is no. The algorithm does not know the distribution. But the interesting thing about zero-sum games is when we solve for our min-max strategy, the algorithm plays its min-max strategy, the adversary plays its max-min strategy, right? We might as well assume we know that distribution because we've solved for it in the game, so that this is the worst-case distribution. Now, if you play something that's not in the worst-case distribution, meaning not in the support of the worst-case distribution, I can tell, right, that you're not in the support. And so that's where I can do better. That is correct. And so I think one of the reasons why I'm excited to present this work is, I mean, look, you know, you want to get intuition for algorithms, and I can get intuition for simple algorithms that the hope is we can then start handling more complex algorithms where it's too complex to get this simple intuition, right? So the hope is something we'll generalize, and we don't know yet.
Is T specified in advance?
Yes. So we're going to be looking at the finite horizon ski renter problem, which is actually not the standard problem. And actually, we'll see that it's important that we are looking at this. So this is a great question. Yeah, we know T in advance. Cool. The next thing that I'm going to tell you about is, and this is more in the flavor of beyond worst case algorithms. So area of mechanism design that has gotten very popular in the last decade is prior independent mechanism design. So this is the situation where there is a distribution over inputs, but we don't know what it is. And we'd like to be robust to any distribution in a large, interesting family of distributions. Okay, so for mechanism design, this tends to be the buyers in your mechanism are going to be IID from some distribution, and you do not know what this distribution is, but you do know they're all IID. Okay, and then you want to be worst case sort of over the distribution that generates the data. And so for the ski renter problem, we're going to do the exact same thing. We're going to assume that good or bad weather is IID from a Bernoulli distribution with some unknown probability P. Okay? And so we'd like to be worst case over the choice of P. Okay, so we can view this also as a zero-sum game where the adversary is now choosing not inputs but distributions. And a mixed strategy adversary is a distribution over distributions. They're randomizing over what P they choose. And then after choosing the P before we go, we play with that probability P, flipping a coin for whether the weather is good or bad. Okay, So, and this comes back to this great question about, well, it's analytically tractable for your simple problem, but what about more complex problems? Actually, for this problem, it's not analytically tractable. We were unable to work out closed-form solutions to solve this problem, this robust optimization problem. So instead of that, we identified conditions under which we could algorithmically solve for them. So could we come up with an algorithm to solve the algorithm designer's problem? Okay, so I want to compute this equilibrium strategy of the algorithm, this mixture over deterministic algorithms that achieves this optimal competitive ratio. And so we identify some conditions that enable us to compute this in polynomial time. And those conditions seem somewhat general, so they could be applied to more problems. And we make use of them to actually compute the solution. And here's a new plot. If I were to compare the worst case algorithm from the previous slide, assuming, again, looking at the equilibrium, so the worst case algorithm versus the worst case prior independent algorithm, it's a big improvement, assuming the IID assumption. Okay, so this is sort of what we get from that. Okay, so this part of the talk is going to be on computational methods for solving these problems when they're too complex to analytically solve. And what are the properties of the problem that enable us to computationally solve them? Is there a question? Yeah, so in the blue, I have the worst case mixed Nash equilibrium for the problem of the first part. Just the ratio calculated. And my axes, what? This is the finite horizon ski renter problem. So I fixed the number of rounds to 9 rounds. We're going to play ski renter for 9 rounds. And I've let the buy cost vary from any real number between 1 and 9. Good point. I should have told you what my axes were in my plot in the previous slide. I apologize for not doing that. It was the same axes in the previous plot as well. Okay, so we're seeing, any fixed buy cost. So the rent cost is 1. The buy cost is some b bigger than 1 in the ski renter problem, which I'll define in a second. So we're seeing basically each point here in this curve is an actual problem specification. And then we're seeing what is the worst case value for that specification. We solve the zero-sum game, and we see what its competitive ratio is, the value of the game. And so here we've looked at worst case inputs, and here we've looked at prior independent worst case inputs. So there's a probability p we don't know. Here, just the whole input we don't know. Thanks for the question. Cool. So the last part of the talk, and this is joint with some additional people, and it was sort of an extension of the second part. We took this same framework and we're like, oh, this should be broadly applicable to situations where we're making decisions without the information we want. And so we applied it to another problem, which is actually a robust information aggregation problem. And I'm not going to tell you too much about that because it's too many different things to have in one talk. The thing I really liked about this was when you do robust algorithms, there's a framework you could look at. So in competitive analysis, we're looking at ratios. So we're looking at multiplicative ratios. So we're sort of trying to say, well, we don't care what scale the problem's on. We want to look at this ratio. But you also could look at additive regret. Like how far are you from optimal at an additive factor, not a multiplicative ratio, right? And you also just could look at absolute performance, right? What's the thing that performs the best in worst case? And I just care about how much performance I get. And so for this robust information aggregation problem, once we have an algorithm that computes this thing, it actually doesn't care what is in the zero-sum, what the objective is in the zero-sum games. You just plug in anything, and you can then solve the game with the different frameworks. And this was really illuminating to see how they were giving us different things. So I want to show you. So again, these are the objectives. So again, the usual min-max over ratios. Here's a min-max over the additive regret, the difference. So the algorithm has a higher cost than the optimal cost. And here you're just trying to minimize the algorithm's cost. Okay, so I'm going to show you plots, and let me just explain what these plots are. So what I've done here is I've taken all instances, basically when you're looking at, I'm looking at the adversary's choice of what's optimal, and I'm sorting them by the adversary's cost. So theta here is the adversary's choice. So if it was the IID ski renter problem, this would be the probability P of the weather being good or bad. Okay, and as a function of the probability P, the weather is good or bad, there's some optimal algorithm. So that's the adversary's choice, and I've sorted it by the optimal performance of the algorithm. Okay, and so that's this blue line is the optimal algorithm, and then our algorithm, our worst case algorithm, solving the zero-sum game, is going to have some bound on its performance, which is this green area. And actually, there could be multiple inputs that give the same, which give different performances. And so that's why it's a region, not just a curve. Okay, so there's an upper bound in the equilibrium that we get from our robust algorithm. And then I said, well, what is its objective in this formula? And let's draw opt scaled by the objective, or like basically what the bound is we're getting. And that's this bound is this cyan line. Okay, and so here you see, and so then the question is like, where is the bound tight in the space of distribution, space of the adversary's choice? And here we see for this robust aggregation problem, the multiplicative ratio is only tight at very small thetas, which correspond to things where you're hardly getting anything good. That's where it's tight. And everywhere else, it's like a super loose bound that we're getting as our approximation factor. So we could have like said, oh, and actually I have like super strong biases coming from algorithms, as I always want to do multiplicative ratio, always, right? And here's a situation where had I done multiplicative ratio, I'd basically be spending all of my time bounding this tiny stuff where everything is bad, right? And most of, so many interesting inputs are here where stuff is good, and we're not getting any reasonable bound on those. Okay, you could have done additive, but additive is sort of the opposite story. Absolute. It's sort of the opposite story, right? Where, okay, look, everything here is going to be less than a quarter. And so, and saying you're less than a quarter is actually pretty easy for this problem. And so we're not really getting any constraint on interesting stuff happening in the problem from absolute. And it turns out that the additive ratio was actually a much better way to look at doing robust analysis for this problem. And you can tell that by looking at how far, when you sort by theta, we get pretty tight to the upper bound. Okay, so when you choose a framework, you're choosing where, what kind of bound you're putting in a plot that looks like this. And you want to choose one where, when you do your worst case analysis, it's really sort of tight in lots of places. And this actually explains why, in algorithm design, we usually want ratio. We usually want ratio because many algorithm design problems are scale invariant. So the way I can make inputs with different optimal values is by just scaling inputs with low values. And if I want things to be tight everywhere for the scaled values, then it's going to be a multiplicative ratio. But this robust aggregation problem is a problem about estimating probabilities that are between 0 and 1. So it's not scale invariant as a problem. And that's why we see that additive is a much better approach. Yes, please. I'm sorry, I didn't hear.
Is this a good time to ask questions, or should I wait?
I love questions at all times.
Okay. Where does did you say like where the bound comes from, or like could you theoretically, could somebody come up with a better bound that's just tighter for A?
Good. So what we've done here is taken the zero-sum game between the algorithm and the adversary, the robust algorithm design game, and we've solved it. And then we said, what does this do on every possible choice? So the adversary is going to mix over a whole bunch of choices, but what does it do on every actual choice of the adversary? And then we've sorted the adversary's choices by its payoff, the adversary's payoff for the optimal decision, and plotted our performance on that actual choice. Okay, and this is finding us choices where, our worst case is tight versus choices where worst case is not tight. Okay, so for additive, the worst case is really tight for all of these choices of the adversary. Okay, whereas for ratio, the worst case is tight only here at these really tiny thetas.
So maybe if your bound was allowed to be like B plus.
This is a great point. So, I was thinking about this just like again, this is a very new talk. I was thinking about this a couple days ago of like, well, in differential privacy, for example, they use epsilon delta, like they have an additive and a multiplicative notion. And maybe you could try to do this framework, such a framework like this with an additive and a multiplicative notion to try to not let this happen, right? I think it's a great idea. I don't know how to do that because that's two parameters and I can only solve a zero-sum game. I don't really know how to do that. But I think it's a great idea. Yes, please.
A couple of questions about the middle plot. How is it possible that the maximum y value goes above 0.25 at the right end of the middle plot, but not the right plot?
Yeah. So what this upper bound is it's this objective has a value. Okay, call that beta here. Okay, then the sort of the teal line of upper bound is opt plus beta. So I just taken the shift and additively shifted it up. And so at theta equal 1, the actual value of opt is 0.25. And so that plus beta is going to be a higher number. Okay? And of course it's not going to be tight here because you're never going to get worse than 0.25 for this problem. Yeah? Good. I think everyone's back. So good. So my agenda is to just give a little bit more details of all these observations that I think were interesting of using the zero-sum framework to understand robust algorithms. Cool. So I've been saying ski-renter a lot, but I hadn't even defined the problem yet, and so hopefully many of you knew about it, but let's go through and make sure we're on the same page. So I'm going to look at the finite horizon ski-renter problem. So here, there's going to be a ski season that has capital T days in it. Each day, it's going to have either good weather or bad weather. And we, after observing the weather, we're going to make a choice of do we buy skis or do we rent skis. If it's good weather, then our buy cost is going to be B if we buy skis and B is bigger than 1. It's going to be 1 if we rent skis. So that's our sort of dilemma. It costs more to buy, but then we don't have to, once we buy, we no longer have to rent. And on bad weather, we don't have to do anything. Okay, so we love skiing so much. If it's good weather, we're going to go no matter what, if it's good weather. If it's bad weather, we're not going. And the question is how long do we rent before we buy, if at all? Cool. So our sequence of days is, x1 through xt. 0 is bad weather, 1 is good weather. A deterministic algorithm at any point in time I looks at the past and makes a decision of renting or buying based on the past weather and the current weather, but doesn't know any future weather. Okay, and a randomized algorithm is a distribution over these deterministic algorithms. Okay, the total cost is just the total cost of first renting and then buying. After we buy, we no longer pay any cost. All right, so we're gonna solve this game analytically, give a solution to it. And the way we're going to do that is first observe that, well, the strategy space is really kind of intimidating, right? Because all algorithms all deterministic algorithms is a really rich space. Right? I said on the previous slide, an algorithm is a collection of functions for every time that maps a vector to a binary decision. And so that's a complicated object. And the inputs are exponentially big as well. And so I'm solving an exponentially big game. So the first thing I'd like to do is not have to solve such a big game. So I'm going to look at a smaller game. And I'm going to solve the game with a smaller set of strategies. And then I'm going to argue that that solution is actually in equilibrium in the bigger game. Okay, in other words, if we're doing the equilibrium of the smaller game, and I say, do you want to deviate to something else if we're playing the bigger game for each player, and neither player wants to deviate if the other player is playing the smaller game's equilibrium. This, I think, is a really key step in, if this is going to be analytically tractable, like reducing the game and solving a subgame that's much simpler is a key step in making this work. And then arguing that that solution to the subgame is an equilibrium in the full game is the necessary thing to do. Cool. So let me tell you what my subgame is. In my subgame, the algorithm is only just going to decide on the following simple set of strategies. So a deterministic algorithm just always buys on the kth good weather, AK buys on the kth good weather day. So if I decide I'm playing algorithm AK, I'm going to wait, count the number of good days. On the kth good weather day, I buy. I don't care what time it is at that time. I just buy on the kth good weather day. And so a mixture is just randomly choosing a K. And then having chosen that K, I randomly buy on the kth good day. Good. What is the pure strategy space of the adversary? The adversary has only good days and then only bad days. So the adversary chooses some number L of contiguous good days. And after the first bad day, it's just all bad. Okay, so the algorithm is choosing a strategy K in 1 to t plus 1. So t plus 1 means you never buy. Okay, and the adversary is now choosing when to switch from how many good days to have. Okay, which is from 1 to t. Much smaller game. Much easier to deal with. And so then the interesting thing to argue is that a mixed strategy equilibrium in this restricted game is actually a mixed strategy Nash equilibrium in the original full game when you can do arbitrary things. Okay? And so I just want to say that the argument you have to make. So I need to basically fix the algorithm from this equilibrium strategy and say, does the adversary get any benefit of deviating? Note that a deviation of the adversary looks equivalent to deciding on L bad weather days, but then shuffling them in between the good weather days. But my algorithm doesn't care about there being bad days shuffled in. It just waits until the number of days and then it buys, right? So basically the adversary doesn't care about this. So the adversary, if it was happy playing its mixture before, if we allow the adversary to mix over shufflings, it doesn't need to. So the adversary is happy to play by its its equilibrium in the smaller game. Okay, Let's do the opposite. Let's fix the adversary. So the adversary is now playing contiguous good and then bad. Well, if this happens, I don't ever learn anything from the adversary looking back in time, so I have no reason to try to update my algorithms. If the algorithm chooses a distribution, right? I don't learn anything from the adversary from what they're doing until the point the game is over, because we have a bad day and it's always going to be bad forever, so now we know what's happening. Okay? And once there's a bad day, the adversary doesn't have any actions. So there are no actions to take anymore. And so the algorithm is also happy to keep what it was doing. There's no way it learned anything from what the adversary did, and so it might as well just keep what it thought it was going to do at the first round, assuming it was contiguous. Cool. So we can solve for what is the equilibrium of this tiny little game, which is now, t plus 1 by t, right, of the action space. And you can solve it basically the usual way you solve for equilibrium is that if you're mixing, the payoffs when you mix have to be equal. And so then you just basically can do some kind of dynamic program keeping the payoffs equal to solve for them analytically. And so we did that. And I think the interesting thing to look at is the probability you put on, this should be k equals 1, I believe. The probability you put on small k is going to be proportional to this number, okay? And small k up to something like t minus flora b. After t minus flora b, we should never buy, because if we just rented for the rest of time, it's going to be less than the buy cost, so it's going to be 0 after that time. Okay, so the ones where you might reasonably consider buying, this is the probability you basically you buy at that point in time. And I put proportional here because there's some normalizing constants to make the probability sum to 1, which we don't care about. But that's the sort of the equalizing probability. This is the amount that if I'm thinking buy now or buy the next day, that's sort of the probability I have to do it at to make the payoffs equal. And another property of equilibrium that helps you do this kind of analysis is that every strategy in the support of a mixed equilibria has to have the same payoff for the other players, given the other player's distribution. So this lets us solve for them pretty easily. It's a question.
So is this baking in, is like assuming that we have full support over those k, or yeah?
So it turns out that you assume that there's going to be full support over those k. And then you can solve for what the answer looks like if you have full support, and then you check that you do have full support. Cool. And so the thing I want to point out here is that this is if you have a short time horizon, this is what you're doing. So if the time horizon is less than twice the buy cost, then you have something interesting to do up until the point where you don't have that many days left versus the buy cost, right? And then you do nothing. If you have a really long time horizon, then actually I just play the infinite time horizon solution. So it turns out this normalization quantity, basically the probabilities lose the t factor when you have a long enough time, and so actually it doesn't matter what the time is. That's what the solution looks like. Cool. Here's the thing. So we restricted to equilibria where the adversary plays contiguous time, good days, and then bad days. It's really easy to tell if the adversary's made a mistake. If the adversary plays a bad day and then a good day, the adversary's made a mistake. The adversary's messed up. And if I haven't bought yet, I can take advantage of that. So let's talk about that. So I want to take advantage of mistakes the adversary makes. I can easily tell if we're not in the equilibrium because the adversaries put bad days in between good days. And so here's the thing. Imagine the adversary is thinking about playing K good days and decides to put some bad days in there. So a bad day is like a no-op. We both just wait, and we are now playing the game after that bad day, but we've lost one time horizon, essentially. So it's kind of like the adversary's decided, hey, let's play a shorter game. Shorter games are bad for the adversary. We can do better the shorter time horizon is. And the thing to do is sort of obvious, right? You just play the optimal strategy as if you had one shorter time horizon. So that's sort of what this slide is saying. So we're calculating these eta t's. We could calculate from the previous probability to like the marginal probabilities of buying, given that you've gotten K good days so far. Okay, that we can calculate from our previous solution. And then what we do is, well, if we played up to time I minus 1, and we're thinking, what should we do in time I? So suppose time I is a good day. Then we look at the number of good days in the past, and we play optimally as if the total game was basically t minus the number of bad days. And the number of bad days is I minus k. Okay, so we basically play optimally for the shorter game. Cool. That's basically all I wanted to say about this. Yeah, and essentially, what's the proof? If you look at, as I said, you want to solve these max-min optimization problems. And if you look at the payoff that someone has if we skip a bad day, or the payoff if we have one shorter time unit, it's the exact same mathematical program. And so the solutions are the same. Cool, and so then we have this picture that I put up before. And so let me try to explain a little bit more about this picture, since I told you there are some things I wasn't telling you last time. So again, I'm going to fix the time horizon to t equals 7 for this point of this plot. We're going to vary the buy cost. So for every time horizon and buy cost, we get a game that we could try to solve. And in green, I have the algorithm we solve for first that doesn't take advantage of the adversary playing bad days. It just looks at the number of good days in the past and plays this probability based on the number of good days in the past. In orange, I have what happens if when the adversary puts a bad day then a good day, we then play the sub-game with a shorter time horizon to do better. So that's that algorithm there. And this is evaluated in expectation over a distribution of our inputs. What is the distribution of our inputs? This distribution of our inputs is the adversary's worst case distribution in the prior independent problem that we're going to solve in the next part. Okay, so I said, what if the algorithm, in part 2 of the talk, the setup was the adversary is going to pick a probability p, and it's going to be IID with probability p. And then there's a worst case distribution over probabilities p the adversary could pick to make an algorithm bad. That's the distribution of input here. And so I can also add to this plot what is the optimal algorithm in the prior independent setting, and that's the blue case. So here we see this is the worst case not taking advantage of subgame optimality. This is the subgame optimal worst case algorithm. And this is the algorithm that's optimal in the assumption the adversary is playing IID. And these are all over the worst case IID adversary.
Can you give some intuition for why the upper curve has much?
That is a great question. This upper curve does something funny between, like, here.
And also between 3 and 4.
This is a very new talk, and we don't know why it's doing this. So that is something we're quite curious about, and we're hoping to figure out soon.
So you solve for non-integral B at what granularity?
I do not know what the granularity is, but it is, I can see that it's at least, I think it's like a tenth. I'm not sure, but it's. Yes, please.
I thought the point of the subbeing perfect was that it was better than the worst case.
That's correct, and we're trying to minimize our competitive ratio, so small is good.
All is good.
And so green is the worst case at the top. Orange in the middle is the subgame perfect, which improves as a lower ratio, so small is good. And if we actually solve the game for the Bernoulli worst case, that's the blue, which we're going to talk about next. How to do the blue. Yes, please.
So it seems like this choice of the ski rental problem was a really nice choice because you could describe this kind of, I don't know, your abstraction or your set of algorithms that would, sufficiently represent the true game in this very nice and intuitive way. Is that going to be true of many online decision problems, or is this kind of special? Like how will we generalize these ideas?
The next part of the talk, I'm going to do the blue, and in the blue we couldn't analytically solve it. And so the hope is that the computational tools that we built to solve it when we couldn't analytically solve it might be useful for shedding some light on more complicated online optimization problems where this agenda is analytically intractable. Thanks for giving me a good segue. Any other questions about this plot? Well, that's unfortunate. I think my battery has died. Cool. So my next agenda is talking about computing these robust algorithms, and this is going to be an example of the prior independent version of the finite horizon ski renter problem. I think this is a really cool beyond worst case analysis framework, and so let's see what it is. There's going to be a family of distributions. Call that kilogram F, and a fixed distribution in the family, we'll call that capital F. We'll draw the input independently over time from this distribution. And so there's an opportunity to learn what the input is from seeing past trials. So we're basically forming a posterior distribution as we go. And that's an important intuition that we're getting at. And one of the reasons why it's sort of hard to solve for these analytically is because we have to do statistics, and we don't know how to do optimal statistics, really. So I think you should expect that we should do something computational. Okay? And now again, there's a Bayesian optimal algorithm. If I tell you the distribution now, and you want to play online, what do you do? And this is where it's important that when I did my notation before, I didn't say it's optimal offline. Okay, it's the whole time opt of x was optimal online, but opt of x, I just told it what x was beforehand, so it might as well do the optimal offline solution. Here, I'm only telling you the distribution. I'm not telling you the full input. So this is a well-defined optimization problem. It's a dynamic programming problem, right? I have a distribution. I'm trying to choose what my algorithm is the best algorithm given my distributional knowledge. So I can just solve this dynamic program. There is a best algorithm. Okay, I'm going to look at a family of distributions which is Bernoulli. So whether it's going to be either good or bad, we'll choose good with some probability p. Okay, and I'm going to look at p between delta, some small amount, and 1. I'm not going to allow delta to be 0 because I don't want to divide by 0 in my ratio. Okay. You can ask, what is this Bayesian this optimal algorithm that knows the distribution? And it's pretty easy to figure out. At time index k, if I've seen k good days so far, if my probability P is at least some ratio of time to buy cost to good days, then I should buy if it's good weather. Otherwise, I don't buy. And if P is below this amount, I just rent the whole time. Okay, so if good weather is high enough probability, buy on the first good day. Otherwise, rent. That's what you do. Okay, and our prior independent problem wants to then solve this thing. I want to find the distribution over algorithms, which optimizes my competitive ratio against the algorithm that knows the distribution. Not the optimal offline algorithm, the algorithm that knows the distribution. Okay, and again, we're going to model this as a zero-sum game. Same as before. Good. If we want to think about computing solutions to zero-sum games, there are a number of computational tools we could start thinking about using. First off, if we have finite action spaces for both players, then this is just a linear program to solve zero-sum games. Okay, there's a wonderful paper about the equivalence of equilibria in zero-sum games and linear program equivalence. Okay. Also, recently, many people studying learning in games have shown that large families of online learning algorithms, like multi-arm bandit algorithms, expert learning algorithms, will converge in zero-sum games to the Nash equilibrium. So we have all these tools for approaching these games. Now, unfortunately, the strategy space of the adversary is continuous and infinite, choosing all possible probabilities between delta and 1, continuous and infinite. And the strategy space of the algorithm is exponentially big. So these are not problems which I can write down this program and just use existing tools. Oh, it's 1 o'clock. No, 1 minute? You think that's reasonable? Well, everyone should go if you have to be somewhere. I'm going to take 1 more minute to just, hey, this might be why it stopped working.
5 minutes is fine because we had a 5-minute break.
Hey, now it's working. Somehow this thing fell out. Cool. So if it was finite strategy, we could just solve zero-sum games. The problem is it's pretty large. And so what we do instead is understand, basically we want to approximate computing the equilibrium. We're going to come up with a fully plenum time approximation scheme, an FP-TAS for it. And we're especially looking for general properties that if they hold, we can then solve this very large game. Okay? So this is the first property we want. We want that there's a cover of the space of the adversary's distributions, where for any algorithm, there's a point, for every distribution, an algorithm's performance is close. There's a cover point where the algorithm's performance is close. And we also want this cover to be not too big. So we want to basically cover the space of algorithm, the infinite space of distributions the adversary could play by close ones. The algorithm now has an exponentially big strategy space, but all we need is to be able to best respond to what nature has done in picking a cover. So if we can basically best respond to distributions over cover points, then we can implement, basically solve the game. We have to not just be able to best respond, we have to also be able to compute the payoffs of best responding. But usually any algorithm you have for best responding is going to come with an algorithm for computing its estimates of its payoffs, and so this is usually for free. So then how does this apply to ski renter? sort of the obvious way. You're going to look at a grid of probabilities, and the point is going to be that for any two probabilities that are close, you really can't tell that I played P or P alpha or P beta if these probabilities are close. And if I can't tell, then it must be the algorithm performance is the same. And it's going to be slightly tricky because we're looking at these ratios, but otherwise it's going to be OK. Yes, question?
Yeah, are you uniformly dividing up the interval?
Yes.
Or, yeah.
And so this lets you get a small grid over the adversary strategy. This is the first step. The next step is computing the thing. And it turns out this is just a dynamic program. You have a distribution over distributions, and your decision variables are the number of bad and good days when you get to some time horizon. You don't care the order they came in because you're just computing a probability P. So your information is the same for any order they arrive in. So there's a polynomial number of decision variables. It's a dynamic program. You solve it with backwards induction, basically. And these are the main important steps. And so we can implement this agenda. We can compare the prior independent worst case with the worst case, and see that we get a lot of benefit in terms of looking at the prior independent framework and sort of the beyond worst case framework. And I think I want to just stop here and call it. That was good. That was very fun. I enjoyed all the questions. Thanks so much.